So, in this lecture of the subject Special Electrical Machines, which is third lecture of this subject for the Akgec students in 6th semester for the subject of Special Electrical Machines, I am going to discuss the two-phase servo motor. A two-phase servo motor is a type of control motor. Basically, it is different from the conventional motors. It is a type of control motor which is primarily used in feedback control system. It possesses the advantages of precise positioning and speed control capabilities. The two-phase AC servo motor is a popular output actuator in a closed-loop system. They possess the advantages of having simple construction, low cost, and requirement of very less maintenance. They are used in various industries because of these features. They are basically the control motors and are employed in feedback control system as actuator. The high resistance rotor in AC servo motors ensures better damping and low inertia, making them highly suitable for precise control applications. A two-phase servo motor is basically a two-phase induction motor, but a specially designed two-phase induction motor so as to serve the purpose of precise control in the feedback control system. So let us start with the basic construction of the machine. So like any other electromechanical energy conversion device, it basically consists of a stator and rotor along with whatever is required to maintain this assembly. So we are having a stator. Stator has two windings. The two windings are placed 90 degrees electrically apart from one another. The one winding is said to be the reference winding or main winding of the motor. It is excited by a constant AC voltage. The second winding is termed as the control winding, which is basically supplied with a variable voltage to control the torque and direction. The material used for stator is laminated silicon steel core to reduce the eddy current losses. The windings are typically made of enameled copper wire, like a normal regular electrical motor or machine. Rotor. The rotor is usually of squirrel cage type with high resistance to achieve a nearly linear torque speed characteristic. Usually it is squirrel cage type, but there are other types of the rotor construction as well. The linear torque speed characteristic, nearly linear torque speed characteristic is the requirement for the precise control of the system. The material used for rotor construction is the rotor bars are made of aluminum or copper. As you must be aware, the squirrel cage type of construction of the machine, it consists of the iron core and slots in the iron core. Along with the slots in the iron core, outer periphery of the rotor iron core, and copper or aluminum bars are inserted in those slots. Then they are connected, they are short circuited with the help of end rings. The material used for making the rotor bars are aluminum and copper. The laminated iron core is used for the core of the rotor, and it is used to reduce the eddy current losses, and a high quality silicon steel is used for reduction of the hysteresis losses. The other parts in the machine are a shaft is there. The rotor is mounted on the shaft, which is supported by bearings. The material used for the shaft is high strength steel or stainless steel for durability and minimum friction. Then we are having bearings. Bearings are the ones who support the entire rotating assembly of the machine. Bearings are used to support rotor shaft and it ensures the smooth operation smooth rotation of the rotor in the air gap of the machine. Ball bearings or roller bearings made of hardened steel are used in these machines. Then housing or the outer frame. The outer casing protects the internal components, stator and rotor. The material used for the outer housing or the frame of the machine is cast iron or aluminum alloy for strength and heat dissipation. Then we are having end covers to cover the complete assembly of the machine. The housing or frame is like a hollow cylinder open from both the ends. So we have to cover it using the end covers. These cover the ends of the motor and provide support to the bearings. The material used is cast iron usually, or aluminium can also be employed for the purpose. Let us just go through the construction, and along with construction, let us now see the working of the motor. So, some more constructional details are summarized over here in this particular slide. Like AC servo motor has a stator and a rotor. Stator has a hollow cylindrical shape and is made up of sheet steel stampings. These stampings are in the shape of circular rings with slots in the inner periphery. They are stacked together to form the core of required axial length. So, if I draw this cylinder, then it would appear somewhat like this, with the slotting along the inner periphery of the stator. This part is said to be the inner periphery, and this part is said to be the outer periphery. Right? The stator core is supported by an outer frame. I just explained on the previous slide. This is also said to be the housing or yoke or the stator frame. The stator slots carry the stator winding, which are of the distributed type. As I have just explained in previous slides, that there are two windings. One winding is said to be the main winding and the other winding is said to be the control winding. A distributed winding, both the main winding and the control windings are distributed in nature, and a distributed winding is required for sinusoidal flux distribution in the air gap of the machine. Now, we may have the 50 Hz motor, or we may have the motors which are required to operate at higher frequencies. So, for 50 Hz motors, the stator is usually wound for 2 or 4 number of poles. For motors which are to be operated with 400 Hz to 1000 Hz supply, the stator may be wound for larger number of poles, 10 number of poles or so, depending upon the frequency. I hope you remember the relation between the two. N is equals to 120 F by P RPM. So, depending upon the frequency of supply given to the stator winding, number of poles would be decided to obtain a particular synchronous speed. Here, this is the representation of the stator. One way of representing the stator is this. Another simplified way with winding on the projected poles. So, here we are having projected poles. Here it is normal cylindrical type of structure. So, this outer frame, this width is representing the outer frame, and this part is representing the stator core, and these are the stator slots. These stator slots are along the inner periphery of the stator core. Two windings which are 90° apart electrically are wound in these slots. The two windings are the control winding and the main winding. Likewise, you can see over here, the one winding is wound over these two projected poles, another winding is wound over these two projected poles. Out of these two, one is the main winding, one is the main winding or the reference winding, another one is the control winding. These motors have two stator windings, reference winding and the control winding. These two windings form the two phases of the servo motor. They are fed with two voltages having a phase difference between them of 90 degree. So, the control winding voltage and reference winding voltage would be at an angle of 90 degree. Let it be, for example, the control winding voltage. Let it be, for example, the reference winding voltage. So, the phase difference between these two voltages is going to be equal to 90 degree. They are fed with two voltages having 90 degree phase difference. In another type of construction, stator windings are provided on salient poles which are fixed on the stator as shown in the previous slide. You can see over here. Now, let us talk about the types of rotor. As I mentioned earlier, usually the type of rotor is a squirrel cage type, but there are other rotor constructions as well and they are in applications as well. So, types of rotor, we are having squirrel cage type, we are having solid iron type and we are having drag cup type. So, the three type of rotor constructions are used in AC servo motors. Squirrel cage type, as you all know, this is the representation of squirrel cage type of rotor construction. They have a thick cylindrical shaped rotor. The rotor core is made up of sheet steel stampings for reduction of the eddy current losses. Along the periphery of ring shaped stampings, holes are provided as shown. So, along the periphery, holes are provided. These holes contain rods, rotor bars, aluminum or copper bars are inserted in these holes. They are throughout the axial length of the rotor. These stampings are stacked to the appropriate length so that holes are along the axial direction, what I have just told you. The circular copper bars are inserted in these slots. These bars are short-circuited with the help of end rings. So, they are short-circuited on both ends with the help of end rings to make a complete rotor electrical circuit. The shaft is usually skewed by one slot to avoid cogging. The cogging may occur due to magnetic force of attraction and you all have gone through all the topic of cogging and crawling in previous semester in the subject of electrical machines too. So, proceeding further, the next type of rotor construction is drag cup type. This type of motor consists of an outer stator core carrying the winding and also an inner stator core. The outer stator core is supported by motor frame as well as the inner stator core is also supported by the motor frame. So, let me show you the outer stator core and inner stator core and the frame as well. So, this part is representing the frame. A part of the frame is extended over here, as you can see this, right? Now, this part is representing the outer stator core. This part is representing the outer stator core and this particular part is representing the inner stator core. See, this particular part this particular part is representing the inner stator core, right? So, the outer stator core as well as inner stator core both are supported by the frame, stator frame. The drag cup rotor is mounted on the shaft. It is able to rotate freely in the air gap between inner and outer stator cores. So see this drag cup type of rotor. It is mounted over the shaft, supported at the bearings, and it rotates between the outer and inner stator cores. The drag cup rotor is made up of conducting material. It is also said to be the drag cup as it is in the shape of a cup. Otherwise, it is a hollow cylinder which is open from one side. It is very thin and light in weight, so the inertia is very small and a good amount of torque can be obtained with the help of this type of rotor structure. The air gap between inner and outer stator core should be minimum in this particular type of motor structure. Now the working of the motor. The working of the motor is based upon production of rotating magnetic field. Here, the rotating magnetic field is produced because we are giving two-phase supply to a two-phase winding, which is electrically apart from one another at an angle of 90 degree. The voltage rating of two windings need not to be same. This is something very important and to be kept in mind. Usually, reference voltage is kept constant and the control winding voltage is variable. The representation of same is shown over here. This is the reference winding, this is the control winding. Control winding gets its input through the servo amplifier, and the input to the servo amplifier is the error signal of the system. You can see here that control winding voltage and reference winding voltage are at an angle of 90 degree from one another. The voltage of control winding is varied as per the error signal obtained from closed loop control system. For speed or position control applications, speed or position error is first amplified by a servo amplifier. I have mentioned over here what actually a servo amplifier. It is also known as a servo drive. It is an electronic device, basically an amplifier circuit that controls and regulates the power supplied to a servo motor based on command signals from the control system. It amplifies low power control signals into high power signals to drive the motor with the desired speed, torque and position accuracy. The amplified voltage is applied to the control winding. The speed is directly proportional to the control winding voltage, and the phase sequence of the voltages decides the direction of rotation of the rotor. If the phase sequence of control winding voltage is leading, if the phase of the control winding voltage is leading or lagging with respect to main winding voltage, the rotor will rotate in one direction or in the opposite direction. The major power to the machine is supplied by the reference winding, and the power supplied by the control winding is very less, as the control winding itself gets the error signal from the system. This results in smaller size and lesser weight for the servo amplifier. Now, for obtaining 90 degree phase difference between the reference winding and control winding voltage, a capacitor is connected in series with the reference winding. This phase shift can also be achieved by using a phase shift circuit. You can see that a capacitor is connected here in the reference winding circuit to obtain the phase difference of perfect 90 degree. Same phase shift can also be achieved using a phase shift circuit. This phase shift circuit would be used in the servo amplifier. Now, the input impedance of servo motor is highly inductive, causing a poor power factor. For its correction, a power factor correction capacitor can be used across the stator winding. Also, modern servo drives are equipped with the active power factor correction circuits. So, for correction of the power factor, these methods can be employed. A capacitor can be connected across the stator winding. They are also equipped with the active power factor correction circuits, and besides this, field-oriented control algorithm of the servo motor operates these motors at good power factor. So the working is based upon production of rotating magnetic field, as I told you earlier as well. When the windings are energized, current flow through them. The currents are having a phase difference of 90 degree and establishes fluxes in the air gap. The resultant flux developed in the air gap of the machine is rotating in nature. The two fluxes are having a phase difference of 90 degree, which can be seen from here. Now this is at certain instants. Let us consider certain instants like instant 1, 2, 3. So the instants theta equals to 0 degree, theta equals to 45 degree, theta equals to 90 degree and theta equals to 135 degree. The resultant magnetic field orientation is this at 0 degree. The resultant field orientation is this at 45 degree. At 90 degree it is here. At 135 degree it is here. So it is a two-pole machine. The machine under consideration is a two-pole machine. So whatever is the difference between these two angles, right? Like it is 0 degree, it is 45 degree. So you will find that the resultant magnetic field has rotated. You can see that resultant magnetic field has rotated by an angle of 45 degree. Here another 45 degree and here another 45 degree. Here we are considering the instants which are 45 degree apart. We can see that resultant flux has a constant magnitude and it rotates. It will have constant magnitude if the control winding voltage is also constant. Otherwise, if there is a variation, it will vary. So we can see that resultant flux has a constant magnitude and it rotates at a constant speed, which is the synchronous speed of the motor. For unbalanced voltage magnitude, the resultant flux magnitude will only change and the speed of rotation of the field will remain constant. The RMF induces an EMF in the rotor circuit, and as the rotor circuit is closed, a current starts flowing. An interaction between rotor current and field gives rise to torque production and hence the rotor rotates. This is the equivalent circuit of a two-phase servo motor. It is just like the equivalent circuit of a three-phase or two-phase induction motor. Here comes the torque speed characteristic of the machine. So in servo applications, the reference winding is supplied with a constant rated voltage and control winding is energized with a varying voltage from the amplifier. The reference voltage is 90 degree out of phase with the control voltage. Under this condition, an unbalance in voltage magnitude only occurs. M equals to Vc by Vr and a set of torque speed characteristic with various values of M. M equals to 1, where Vc would be equal to Vc is equal to Vr, and for other cases, the reference winding voltage, which is constant, is more than the control winding voltage. With a further reduction in the control winding voltage, you will find that the torque speed characteristic is shifting in this direction. But the shape of the torque speed characteristic remains same. It is almost linear. These are the various applications of servo motors. They find application in robotics, in CNC machines, automated manufacturing and conveyor systems, camera autofocus and gimbal stabilization, in aircraft control systems, then in textile and printing industry for the precise positioning of fabric rollers, print heads and embroidery needles, medical equipments, automotive industry, smart home and automation. Smart home automation. So these are the various applications of a two-phase AC servo motor. These are the general applications of servo motors. And for here we have discussed about the two-phase or AC servo motor. So that's all for this lecture. Thank you.